Welcome to another edition of Sparky Help, this time the easy guide to electrical phasor diagrams, and we'll look at resistive, capacitive, inductive circuits in both series and parallel. Please like, share and subscribe. So what is a phasor diagram? A phasor diagram is a graphical representation of a sinusoidal value, which is basically a sine wave or any other waveform it happens to be, at a point in time at a given frequency. So this can be a graphical method of showing just that. So as always, let's look at a particular circuit. So here we have a resistive circuit, one component connected to a 50 Hz supply. And if we apply Ohm's law, we can work out the current, and the current in this case is 6 amps. So let's look at what the sine wave would look like for this. So there we have the current, and it starts at 0, goes through 180 degrees, goes through 0 again, goes negative, and then 360 degrees. Remember, this is how electricity is generated. And there we have our voltage, and voltage goes through 0 at exactly the same points. When one peaks, the other peaks. So what does a phasor diagram represent? Well, a phasor diagram can represent this sine wave, and it's an easier way of displaying it. So as always, what we have with a phasor diagram is we start with a reference point, and in this case it doesn't matter because it's one component. So I'm going to use the current as the reference, and this is a line that's drawn from left to right on the horizontal, and it's any length of line, it doesn't matter what it is, and we call it I reference. And because this is representing a thing rotating, it goes in an anti-clockwise direction. Don't ask me why, but it's the convention we go with. It's anti-clockwise. How much is it rotating anti-clockwise? Well, it's rotating by 50 Hz ultimately, but what it actually is, because it's a angular velocity, it's based on something called radians per second, which we convert by 2 pi f. 2 pi f you may sometimes see written or abbreviated by the lowercase of an omega symbol, and it's this one, it's omega. So not to be confused with the uppercase, which is used for ohms. So there we've got the angular velocity, and we've got a reference point. So what we now need to show on this is what the voltage is doing. So what is the voltage doing? Well, it peaks at the same time, and all of these, remember, can be drawn to scale. And there's our voltage. It's in phase with it. So we would draw it along those lines to a given value if that's what we wish to do, and we can label it, and V equals 120. As you can see, drawing two lines on a page or anywhere is much easier than trying to draw the sine wave that it actually represents. So the angle between the voltage and current is 0. It's said to be in phase. But that could also be used the other way around on this particular one. We could make V the reference, and there we've got it the other way around, and now we've got the current shown, and we can say the current is in phase with the voltage. It doesn't matter because it's one component, so either or is acceptable, but the point being it's anti-clockwise, left to right, 2 pi f or omega. So let's look at a pure inductor. Pure inductor, remember, is a theoretical device, effectively. A pure inductor has no resistance. And I've got XL for this pure inductor is 20 ohms. So applying Ohm's law, we can do V divided by XL. 120 divided by 20 gives us 6 amps. To help us with the phasor diagrams, we can use this word here, civil. How does that help us? Well, we're going to look at only 3 letters in this particular word. And this is an inductive circuit, so we're going to look at the last 3, which is VIL. L being inductive. The V in this case stands for voltage, and the I, well, you guessed it, I hope, and that stands for current. And if we look at this, then V is in front of I in L. So in an inductive circuit, V leads current. And that's basically how we'd look at this one. So it's a good way of trying to remember which direction all this goes. Why do we do this? Well, this is a pure inductor, so let's look at the sine wave again. And now you can see that the voltage and current are out of phase with each other. In fact, go look at my video on inductors and you will see how it will help explain why this occurs. But if you look here, then when one is at peak, the other is at 0. And this happens on a regular basis every 90 degrees. One is at peak and one is at 0. So it's out of phase. And if we look at it, it's out of phase by 90 degrees because the other one doesn't go through 0 until 90 degrees later. And if we go back to bottom, the civil part, the V is in front of I, and in this case it's out in front of it by 90 degrees in an inductive circuit. So this is quite difficult to draw all the time. As you can see, nice and easy to do on here when it's been set up for you, or I've set it up. But to draw it, that will be quite tricky. And this 90 degrees not so bad, but when it's not 90 degrees or 80 degrees or 70 degrees, it makes it more difficult still. So phasor diagrams are the chosen method. So what do? We start off with a reference line. I'm going to start with current as our reference. So remember, left to right, any length of line. And we label it I reference in this case because this is a point we're measuring from. It goes in an anti-clockwise direction. So this is a rotational line effectively, but we've got it at a point in time. It's rotating by 2 pi f or omega. Now where does V go? Well, V is in front of I. How many degrees out? Well, this is a pure inductor, and as we can see on the sine wave, it's out by 90 degrees, so it goes vertical by 90 degrees. And that can be drawn to a length if you were so wish, and that equals 120 volts. So there we've got V is in front of I by 90 degrees, and this phasor diagram we see here represents the sine wave above. Which one's easier to draw? The bottom one, obviously. But because it's one component, it doesn't have to be drawn as I as reference. In this case, we could have V as the reference. So again, left to right, V ref, rotating by an angular velocity of 2 pi f or omega, and remember, V is in front of I. Because I've made V the reference here, I will be behind it by 90 degrees. Remember, all of this, if you imagine these all move together, so they always stay 90 degrees apart. And there we've got our current of 6 amps. So there we've got a phasor diagram for this particular circuit. Because there's only one component, it can be either one of those. So let's look at the third one. Let's look at a pure capacitor. And again, if you're not sure how capacitors work, I have a video on capacitors. Go check it out. And then we've got an XC on this one of 20 ohms, so we can work out the current. So we'll apply Ohm's law. And we've got V divided by XC, which is 120 divided by 20 gives us 6 amps. So the current in this one is 6 amps again. We're going to use this word again, civil, but this time we're going to look at the first 3 letters. CIV, the C standing for capacitive, I being current, and V equals volts. So in a capacitive circuit, I leads V. And that's how we read this then. So if you've got an inductive circuit, you look at the last 3. If it's in a capacitive circuit, you look at the first 3, and it's whichever is dominant out of all of it. So as always, then here's our sine wave that this represents. Because it leads, now you can see the current is out of phase by 90 degrees again. So when one is at peak, the other is at 0. And this happens 4 times in one complete cycle. And this time the current is in front of the voltage by 90 degrees, which is a bit weird, but then go look at how capacitors work. You have the voltage at 0, but you have a maximum current. So we'll start off, we'll make I the reference, and that goes from left to right. I ref, it's rotational, and it's rotating by 2 pi f. Because we go back to the civil thing again, I is in front of V. So if I is on the horizontal, for it to be in front, V must be down. And we would draw that to scale, or we could, and it's out by 90 degrees, V equals 120 volts. And that's out by 90 degrees. But we could also draw it the other way. As it's one component, we could make V the reference, and there's V the reference, rotates by 2 pi f, and looking at CIV, I is in front of V, so V is the reference, so therefore I must go up by 90 degrees, and we can label that as such. So when you have one component like this, the phasor diagram could be either or of those. It makes no odds. They're both correct because the representation is still correct. Then we get a little bit more tricky. We've got a series resistive and inductive circuit. So there's our circuit, and we've got the voltage across the resistor, the voltage across the inductor. And we're going to use the word civil again. So this is an inductive circuit, so we're going to look at the last three letters, VIL. So volt leads current in L in this inductive circuit. In order for this to plot this one, I'm going to give you the voltages across each of these components. So VR would read 40, VL would read 113. Now this is a series circuit, so when we draw the phasor diagram this time, we're going to make whichever unit out of volts or current stays constant for all the components. And in this case, it's a series circuit, so current stays constant. So we make I our reference and we draw it left to right. And because it's the common unit and it's the same unit that passes through all those components, it doesn't matter what length it is, because once you've calculated it, that's the value for all components. The value that does change is the voltage. So we call this I reference. And we could work out what that would be if given more information. It's rotating by 2 pi f in an anti-clockwise direction. Now we can plot these two voltages on here. For the voltage across the resistor, well, in a resistive circuit, the volts across the resistive part was in phase, so that would be drawn in line, and that can be drawn to scale. And there we've got VR equals 40 because it's in phase with I. Go back to look at the first one. Then in the inductor, we use VIL. So the voltage leads the current. And at that part, when we draw it like this, is a pure inductor. And it's out by 90 degrees. So volts is in front of the current by 90 degrees. So that goes up. And we've got 113. And these are drawn to scale on this one. That leaves one component to find. And that's the phasor sum of VL and VR of these two values drawn to scale. So we'd measure them, and then the diagonal that we would get would be VS. And if we draw this to scale, and this is drawn to scale, or a scale, and that equals 120. And if we look at that, that would give us, put a protractor on, we can get the angle. So it's approximately just over 70 degrees as the angle. So that would give us something called the power factor from that. And there we've got to have angle, and therefore the voltage and the current in this particular circuit is out by 70.5 degrees, approximately. And that's what phasor diagrams allow us to do. Without picking up a calculator, we can measure them all. And remember, a resistor and inductor, effectively that's a real coil, because a real coil has got resistance, and therefore you don't separate them. We can separate them on paper, but a real coil contains resistance and inductance. Let's look at a series resistive and capacitive circuit. So for that, we'll give you the voltages again. So VR equals 60, VC equals 104 on our supply, which is 120. And we're going to use the word civil again. And this time we're going to look at the first three. Capacitive, I leads V. I leads V if it's pure by 90 degrees, but either way it's in front of it. So as always, we're going to put a reference line, and the reference, because it is series, is I, and there we're going to draw it left to right, call it I ref, and remember it rotates in an anti-clockwise direction. So we're going to plot on there the VR. Now VR is in phase with the current, and we can draw that to scale, and VR equals 60. VC, the pure part that we've got on the right hand side, is out of phase by 90, and go down to the civil again. In a capacitive circuit, I leads V. Well, I is on the reference, so V must be going down, and it's out by 90 degrees, so the VC is 104 straight down. What we need then is 120, and that would be the phasor sum of those two. So put the diagonal in, and that then, if this is all drawn to scale, remember I have done, is VS is equal 120. We can put a protractor on again, and we get an angle, and it's approximately 60 degrees. So the current leads the voltage by 60 degrees, or you could say the voltage lags the current by 60 degrees, but generally we refer to what the current is doing. So the current in this case leads the voltage, the supply voltage, by 60 degrees. What about a parallel circuit? So now we've got a parallel circuit, two resistors in it, and in a parallel circuit the bit that stays the same is the voltage, and it's the currents that differ. So we can work out the currents in the different branches like this. So using Ohm's law, because the values are the same, to find I1 and I2, which are the two branches, therefore we've got 6 amps in each of those branches. To draw the phasor diagram, because it's a parallel circuit, we draw voltage as our reference because both components have the same voltage across them. So we'll call it Vref. We know it's 120 because the drawing tells us. It rotates by 2 pi f at an anti-clockwise direction. And there we have it. And now we've got to plot on, we can plot on the I1, which we can put there, which is 6 amps. And then added to that, you have I2, which is also 6 amps. To find IT then, it's the phasor sum of both of them. Because they're all in the same direction, they're all in phase, they are literally added. So they literally draw the line, and therefore IT is the sum of both of them, which is 12 amps. This is why if you're doing series resistances, you're not taught probably how to do phasor diagrams, because all you'd be doing is drawing straight lines on top of straight lines, and you'd probably think, what's the point of this? But there we have it. Let's look at parallel resistor and an inductor. So we can work out the currents for each of these by using Ohm's law, and it's either V divided by R for the R1 or V divided by XL, and that will give us the branches, and they happen to both be 6 amps for both. So I1 and I2 both 6 amps on the given values that I have. So because it's parallel, voltage is our reference. Now I1 is a resistive part, so it's in phase. Remember, all this is going round in an anti-clockwise direction. We can measure this on here, so let's do a measurement on this one and we can draw it to scale. 6 amps, and there it is. That's I1 because it's in phase with it, and we can label it as such. The inductive part, using our word civil, remember, the volt leads the current. Well, voltage is our reference. The current is out of phase on this part by 90 degrees. So we can draw a line directly down and measure it, for this one also to be 6 amps. And this one is our I2. To find the total current, it's the phasor sum of both of them. And then join it up, measure the line, and there we see our I total of approximately equal to 8.5 amps. What we can now do is measure the angle between that, so that is approximately 45 degrees out of phase. Now let's look at a parallel resistor and capacitor. To find the currents, we apply Ohm's law. Because the voltage is common across all, becomes 120 divided by 20, and we get 6 amps on each one. So I'm trying to keep it relatively simple. Voltage stays common, so we draw Vref rotating by 2 pi f in an anti-clockwise direction. We can draw the resistive part, which is 6 amps, which is in phase, and we can draw that on there and label it as such. We can use our word civil again, and this time it's a capacitive circuit. I leads V, well, V is our reference, I is in front. How much in front? It's 90 degrees for this particular part because it's the pure component. So 90 degrees up, we can draw our other 6 amps. And this is our 6 amps through I2, which is for the capacitor. Join them up and then draw this line in. And this line then will become our current IT. It's the phasor sum of both of those. So it's approximately 8.5 amps. We can get our protractor and we can work out the angle, and again it's 45 degrees. So therefore what we can say is the current leads the voltage in this circuit by 45 degrees. So I hope this has helped. Easy guide to phasor diagrams. This is Sparky Help. Thank you very much.